So where does the camera see up to?
I can adjust the camera, but
I'll only use this. I'll only use this half.
oh, I thought you said you didn't need one. Sorry.
Oh, a slide advancer. I thought you meant.
Sorry.
I thought you meant the screen to see the next slide. Sorry. Closer, quicker. Okay, sorry. That's good. Okay.
Okay, so you are everybody ready? Okay, so so let me open up. So the next speaker is Krupa, and he will talk about well-posedness for hyperbolic systems of conservation laws.
Thank you. What's this? Okay. So I'm Sam. I'm a postdoc here. I'd like to thank the organizers for giving me an opportunity to speak. So my work is about hyperbolic systems of conservation laws. It's a PDE I study, and the space dimension I study in is a connected sum of 6,435 copies of the octionic projective plane. No, I'm kidding. This is from Sasha's talk, but I study conservation laws in one space dimension. And this is actually a pretty interesting story already. So my talk today will be about the well-posedness theory for hyperbolic systems of conservation laws in one space dimension. And we'll be discussing how entropies.
Try putting it into slideshow mode instead of full screen mode. Sometimes that works better. Sometimes it doesn't.
Okay.
I don't know why.
So let me, for the rest of my talk, so now let me explain the well-posedness theory for conservation laws in one space dimension, sort of what the best stuff is so far. Then I'll discuss the advances that I've made. So the best theory so far is from Bresson and co-workers, and they study solutions with very small BV initial data. And they study solutions in this class. They have existence, uniqueness, and well-posedness in this class of solutions. And they measure distances, the Bresson and co-workers, they measure distances in L1. But their theory is somewhat limited. For example, for 2x2 Euler system in one space dimension, we have existence of solutions with large data. So we have large data solutions. And it'd be interesting to consider the stability of solutions in this large class. So to expand past the L1 theory, to move on to something different, we consider the L2 theory, where we measure the distances between solutions in L2. And this is we're going to use the relative entropy method and something called the theory of shifts, which I will discuss. So the point here is that it's harder to be in L2 than in L1. So for example, this is a function which is in L1, but it's not in L2. So the L2 norm contains more information. It's harder to measure things. So when I'm going to develop this relative entropy method, I'm going to have to somehow relax my notion of stability to take care of the more difficult norm. I'll discuss that.
The space would be compact.
No, so right. So the space will not be compact and the functions will not be infinite. I give this just for flavor. Yeah, thanks. Okay. So the key difficulty with this thing is that for systems of conservation laws in one space dimension, you often only have one entropy. So a physical system will often only have one entropy. And this is one of the key roadblocks to a stability theory. But the relative entropy method, which I will discuss, the key point is that it only ever uses one entropy, and it's a very deep, powerful theory, and it can consider solutions with very large data. So the well-posedness theory I will discuss will have no small data limitations. And this relates to the theory of shifts, which I will discuss. Okay, so for the rest of the talk, I will use as my toy equation burgers. But of course, this is simply a toy example, and I use it as a simple example just to convey ideas today in this talk. But I always have in mind physical systems such as compressible Euler, shallow water, isentropic Euler. Okay, so I'm just using burgers just to get my ideas across. The burger system is the following. So U is the unknown. It's the function of, like I said, space, not the octaionic plane, but space in one variable, and time. The function U is it gives us some distribution of a conserved quantity that we're interested in. U0 will be the initial configuration of this conserved quantity on the real line. And the flux function A will be in C2 and strictly convex. And it explains how our mass moves around as a function of time. We'll consider both classical and weak solutions. So classical, like they have smooth and they have derivatives, and weak in the sense of distribution, so multiply against a test function. So this is not elliptic theory. There's not necessarily a regularizing effect. So we really will have solutions that are not differentiable, not even continuous. So we really need to consider weak solutions. Okay. To get the classical Burger's equation, we take the quadratic flux. Yeah, right, sorry. So I should say that just as I stated it, this equation is already ill-posed. I can give the following example. So just for Burger's flux, consider the following initial data. So this initial data, because plus and minus 1 both square to 1 with the Burger's flux, we see that both these terms would be 0 if I take a steady state solution. This is U0 x. This is one possible solution, but a second solution would be the refraction fan, which at time 2 will look like this. So it's spreading apart. It wants to pull apart the left and right hand states. Okay.
Not a steady state in the sense of distribution. It's not a solution in the sense of distribution.
It's right. That's a good point. So it's actually right. So this is the first example of I gave already an example where we need a distributional notion of solution to make sense of it. But I mean, the intuition is that if plus and minus 1 both square to 1, then this will be 1. I mean, this will be 0 because it's steady state, and this whole term will always be 1. So its derivative in space is 0.
But we will have a delta function anyway, so it's not a weak solution.
No, the natural Rakhine-Ganiot speed would also be 1 minus 1 over 0. I mean, 1 minus 1 over 2. So it would be a shock with speed 0.
Oh, you're right. Yeah.
So the Diracs cancel.
Yeah.
The Dirac in the time direction cancels the Dirac in the space direction. Yeah. But it's not entropic, right? Okay. Okay, so the way we recover well-posedness is entropy conditions. So the idea is that we want to impose a physical condition, so the second law of thermodynamics, and hope that by imposing this condition on our solutions, we get a smaller set where we have some stabilizing effect from imposing an entropy condition. So in the scalar, it works in scalar and systems similarly, but I'll present it for scalar. So for a scalar system like Burger's, we have a pair of functions, eta and q. Eta is the entropy, q is the entropy flux. And for the system, they're related like this. So we say that q is the entropy flux for eta if the derivative of q is the product of the derivative of eta and the derivative of our flux function a. And for us, we'll say that a good solution is a solution which satisfies this following entropy inequality in a distributional sense. So in physics, you want the second law of thermodynamics says that physical entropy is increasing, but in math, we take our entropies to be the negative of the physics entropes because we want our entropies to be convex instead of concave. So for us, good solutions will have mathematical entropy decreasing. And we hope that this will have some stabilizing effect, some sort of stabilizing effect. So for Burger's and scalar equations, there's two famous theories of uniqueness and well-posedness. The first one is Kruskov's theory using many, many entropies. And so the point is that this equation for any eta, I know I always have a q in the scalar case simply by integration. I can always just integrate and find a q. So Kruskov takes advantage of the fact that every eta gives a q for the scalar case. And Olenek in 57 proved and discovered her condition E, which gives existence and uniqueness for solutions which satisfy her one-sided Lipschitz estimate. And this one-sided Lipschitz estimate says that for Olenek, a good solution for a scalar will either have a down jump or be spreading out. So coming back here, this is an up jump, right? So Olenek says this is the steady state's the wrong one, and the refraction is the right one. It's spreading out. So that recovers well-posedness in the scalar case. And these two theories are equivalent when the Kruskov theory and the Olenek theory are equivalent when the flux function is uniformly convex. So for the system, so thinking like compressible Euler, isentropic Euler, shallow water equations, the P system, some sort of physically motivated system. For systems, you have two conditions on solutions which give you uniqueness. So if you have a solution with very small initial data, BV, small initial BV data, so barely allowed to wiggle, like basically constant, and it's entropic, and it satisfies either the bounded variation condition, which is a condition on space-like curves in time space, or the tame oscillation condition, which says that your solution, the oscillation is locally controlled by the variation of the solution. If you have either of these conditions and you have small BV, then you know that you're unique in this class for systems. Okay, but now this does not answer the question, for example, about large L2 perturbations. This does not discuss large L2 perturbations, which exist in the 2x2 case, such as isentropic Euler. So let's now move to the theory of relative entropy. So the theory of relative entropy was something introduced by de Fermos and Diperna, and it says what they were able to get weak, strong stability estimates, which said that if you have a weak solution entropic for one entropy and a strong solution, so differentiable smooth, they can make stability estimates between these two solutions as long as you had one convex entropy. And what they did was they took the one entropy they have and they would consider the relative entropy, which is simply hyperplane correction. And it's an L2 theory because this is an L2 quantity in some sense. Okay. Right. So what they did was their estimates say that if you integrate this relative entropy in space, they would give you the growth in time of this quantity. When this is a rough solution, an entropic, rough, weak solution, and this is a smooth solution. And the relative entropy method is a very deep theory. It's powerful, it's deep. You can put in basically any L infinity entropic function here, and you get a stability estimate. But we want to consider stability between two weak solutions. So to move in this direction, the idea is to insert discontinuities into this solution, which normally has to be smooth. And for a long time, this was not thought to be possible. So let me explain what can go wrong if you have a smooth solution, but with one discontinuity. Let's consider burgers, and let's see if we have growth in this L2 sense. So consider a smooth solution, but now we have a discontinuity. So this would be our U bar, but now we've introduced a discontinuity. This is burgers. Again, we have plus or minus 1. They square to 1. So again, we have we can have a steady state solution, but it goes the other way than this one. So Olenek says that this is actually going to be the proper steady state. So the entropic solution here will be a steady state. Now let's take a rough solution, a perturbation, a guy in the first slot of the relative entropy, the first slot. So that'll be this guy. And at this point, we made an epsilon perturbation in height. But this gives us an epsilon perturbation now in speed at this discontinuity. So now we have a shock moving to the right with speed epsilon over 2. At time 1, the rough perturbation, it causes a large movement in some sense. And in time 1, we actually get a large orange region, which gives us a square root of growth phenomenon, square root of epsilon growth phenomenon in L2. So we appear to have lost L2 stability. We regain it in the following way. We allow U bar to move with an artificial velocity. And if we allow it to move with an artificial velocity, we can perturb its velocity to meet the perturbed velocity of the rough solution in orange. This will actually kill all L2 growth. And this is the theory of shifts. This was a program initiated by Vasseur in 2008. And the first result was by Leger in the scalar case in 2011. So this notion of having an artificial velocity, it means that you're no longer a solution. But it somehow gives us a relaxed notion of stability, like I mentioned at the beginning of the talk, where I had the L1 and the L2 theory. So this is the relaxed norm we need to measure in L2, because there's some difficulty. So Leger proved, this is a picture of what Leger proved. Leger proved exactly what I said. If you have a shock, you can actually not take even just a simple perturbation like I showed. You can take any very rough L2 perturbation, like in orange here, and you can move the blue guy to kill all L2 growth relative to the orange guy, as long as the blue guy can move artificially. That's what Leger proved. So this is a program. The theory of shifts is a program. It really showed that the relative entropy method can be extended and improved in a surprising and unexpected way. And the latest result is the following. So this is a theorem with myself and Gang Chang at the University of Kansas and Alexei Vasseur in Austin. And then we actually had to split the result into a second paper with really a tour de force of the theory in the paper with Will Goulding in Austin and again, Alexei Vasseur. And we show that for a 2x2 system of conservation laws, you can think the isentropic Euler with gamma greater than 1 solutions, which live simply in the space of L infinity and with small bv initial data, and are entropic for convex entropy and verify a trace condition weaker than even BV loc. These solutions will coincide with the well-known BV, small BV solutions. So this result actually says that the tame oscillation condition and the bounded variation condition, which I gave as the state of the art, they're no longer needed in the case of 2x2 systems with a convex entropy. So this actually shows that small BV solutions are stable not only in the class of tame oscillation condition and bounded variation condition, but they're stable even when you consider them in the large class of L infinity with a weak trace. So it shows that in a much larger class, you don't lose well-posedness of the 2x2 system. And this comes from simply allowing, this comes from not simply, but from technology involving letting the smooth solution in the relative entropy converge to the rough solution and introducing discontinuities and shifts. Okay, so my current work involves applying the L2 type theory, which I've just discussed, to numerical calculations to show that the solution in the computer can stay close to the exact solution. This is current work with Jan Wieselman and his group in Darmstadt. And then furthermore, I was a postdoc of Professor Seklihidi in Leipzig for the past year until I got here. And we're studying possible well-posedness of these 1D conservation laws via the technique of convex integration. So that's it. Thank you very much.
Thank you.
To explain the sheet in the case in which you have one single jump, right? But if you have many jumps, somehow you will have to adjust, say, also like the width of the domain because you're traveling in different ways. How do you do it?
So we implemented the program first for burgers, and my first homework assignment from Alexei Vasseur was to solve exactly that problem, and this was my solution. So we do a one-dimensional, we do a scalar front tracking scheme. So let's actually use the same colors as I used there. So the rough solution is an orange. I construct a more regular solution in blue with the following property. It's Lipschitz increasing with down jumps. These are actually dense in L2 loc, these blue guys, they're Lipschitz increasing with down jumps. And I put a shift, these go into the smooth slot of the relative entropy, the blue guys, like in my pictures. I put a shift to each one of these discontinuities. And what I do then is for each blue guy, I extend it globally to a increasing function globally defined on R. Every one of them, I take the solution with that initial data, and the shifts now simply glide back and forth between the two solutions, exposing one when necessary, not exposing the other when not necessary. And this works because if I make the extensions, that way they're globally ordered, like this one is always on top of this one. And this one's always below the previous one. Then because the jumps will always, no matter where the shift decides to go, like here or here, the ordering will always be entropic according to condition E, and I can always build a shift. And so I can just extend some of these domains and when I want to move the shift around locally at each of them. Now you're wondering, well, what happens when two shifts touch? Then I delete the middle solution in the middle and restart the clock. And this actually gives me a sequence of functions, which stay, and they're not solutions to anything, but it gives me a sequence of functions, L2 close to my rough initial data, but with a landing condition E. So that transfers condition E to my rough solution, and that gives me uniqueness.